tiny 7mm traveler from beyond, our solar system has just ripped through our cosmic backyard, moving at 137,000 miles per hour, carrying elements that should not exist anywhere in nature. Astronomers are calling it 3 Atlas, and it's forcing us to rethink what truly drifts between the stars. This is no ordinary comet. It breathes carbon dioxide instead of water, bleeds nickel without iron, and has endured longer than most galaxies have even existed. If you're drawn to the strange, the impossible, and the discoveries that shatter our understanding of the universe, you're in the right place. Get ready, because this cosmic visitor is about to change everything we know about where stars end and mysteries begin. 3 Atlas appeared in our telescopes like a cosmic missile, moving faster than anything natural should ever move. Measuring 7 miles across, this interstellar wanderer dwarfs every space visitor we've ever encountered. To put that into perspective, if the famous Oumuamua were a single grain of rice, 3 Atlas would be a bowling ball. The size difference is so extreme that astronomers estimated we should discover 10 million smaller objects before ever finding one this massive. Yet here it is, calmly breaking every statistical model we've built about what drifts between the stars. And its speed tells an even more dramatic story. 3 Atlas tears through space at 58 kilometers per second, carrying what scientists call hyperbolic excess velocity. Behind that technical phrase hides something violent. This enormous shard of rock and ice was launched by catastrophe. Whatever hurled it away did so with enough force to escape not only the pull of planets, but the gravitational grasp of its own star. What kind of cosmic disaster can create such speed? Imagine giant planets locked in a chaotic dance, their gravity slinging smaller worlds into the void, or a dying star, swelling in its final moments, its expanding atmosphere sending shockwaves that blast ancient comets into interstellar darkness. 3 Atlas bears the frozen scars of that violence, a relic of destruction, drifting for billions of years. Its discovery reads like science fiction. The Atlas telescopes in Chile scan the night sky repeatedly, using artificial intelligence to catch anything that moves against the static sea of stars. On July 1st, 2025, an algorithm flagged something strange, a fast, massive object cutting across the heavens. Within hours, observatories worldwide turned their instruments toward the mysterious intruder. The data stunned everyone. 3 Atlas follows a hyperbolic orbit with an eccentricity of 6.141, meaning it will approach our sun once and never return. But the strangest part wasn't its path. It was its angle of approach. This interstellar visitor was coming from a direction almost perfectly aligned with the plane of our solar system. A coincidence with less than a 0.2% chance of happening by pure randomness. Astronomers began to whisper about statistical impossibilities. An object this large, moving this fast, arriving from this direction simply should not exist according to every known model of comet ejection. 3 Atlas had declared itself as something far beyond an ordinary comet, an anomaly that might rewrite the story of what lives, dies, and drifts between the stars. And yet the true surprises were only just beginning to emerge from the darkness. 3 Atlas carries the unmistakable fingerprint of cosmic violence, its impossible speed, a relic of something catastrophic. When astronomers measured its 58 kilometers per second of hyperbolic excess velocity, they knew immediately they were witnessing the aftermath of a traumatic ejection from its birth system. That speed isn't random. It's pure, unrestrained kinetic energy, the mathematical scar of an object that broke free not only from the pull of planets, but from the gravitational hold of its parent star itself. It's like a bullet fired with such force that it not only leaves the barrel, but escapes Earth's gravity entirely, vanishing into eternal space. The physics behind this velocity points toward nothing short of catastrophe. Computer simulations suggest that to reach such speed, 3 Atlas must have encountered giant planets, at least as massive as Jupiter, whose immense gravity turned ordinary motion into chaos. Picture it. Billions of years ago, 3 Atlas was a quiet, frozen body, orbiting peacefully in some distant solar system. Then, its serenity shattered. Massive planets began to migrate inward, their gravitational tides rippling outward and disturbing the fragile harmony of comets and asteroids beyond. The system became a celestial billiard table, where smaller worlds were flung about like marbles. Most met violent ends, crashing into planets or drifting away at modest speeds. But every so often, gravity aligns with terrifying precision, creating what scientists call a gravitational slingshot effect. In that rare alignment, 3 Atlas would have been caught in a perfect storm of force, accelerated to unimaginable velocity, and hurled out of its home forever, doomed to wander the interstellar dark for billions of years. Some astronomers, however, envision even more dramatic origins. One theory imagines 3 Atlas forming in a binary star system where 2 suns orbited each other in a delicate balance. As the stars aged, one might have swelled into a red giant, its expanding atmosphere creating deadly pressure waves and intense radiation. These forces could have ripped through the system, blasting smaller objects into the void with explosive power. Others suggest an even rarer possibility, a stellar encounter, 2 entire solar systems brushing past one another in deep time. The gravitational chaos from such a meeting could easily tear planets from orbits, strip comets from stars, and hurl survivors, like 3 Atlas, into eternal exile. Whatever the truth, its speed tells us this: 3 Atlas was born in violence, baptized in gravity's fury, and condemned to roam the cold between stars, carrying within it the memory of a destroyed world. Our galaxy holds over 100 billion stars, each orbiting the galactic center in vast, intricate paths. Every so often, 2 of these star systems drift close enough for their gravitational fields to collide, briefly entangling before parting again. In these rare encounters, the smallest bodies, comets, asteroids, frozen worlds, can be flung outward at incredible speed, cast into the space between stars like cosmic exiles. The velocity of 3 Atlas tells a story not just of motion, but of time itself. Moving at 58 kilometers per second, this traveler has likely been adrift for billions of years, crossing the void between suns. Out there, between the stars, the universe is not gentle. Cosmic rays shred surfaces atom by atom, while the faint winds of distant stars erode all that remains. Yet somehow 3 Atlas has endured, its body scarred but unbroken, its heart still intact. It drifts now like a time capsule from another age, its chemistry frozen since an era when our galaxy was still young, when ancient suns burned hotter and worlds were made of stranger stuff. Locked within its icy core may lie the fingerprints of a time before our solar system existed, when planetary formation obeyed, rules long vanished from the modern cosmos. The mathematics of its orbit point toward a birthplace deep within the galactic thick disk, a realm of ancient stars that formed during the Milky Way's chaotic youth. These old systems contain far fewer heavy elements than our Sun, suggesting that 3 Atlas was born under conditions utterly alien to our corner of space, in a world where iron was rare and hydrogen and carbon ruled. But perhaps the greatest mystery isn't where it came from, but how we found it at all. Objects like this are nearly invisible, dark, cold, and impossibly small against the endless sky. By every calculation, 3 Atlas should have passed unseen, forever lost to human eyes. Yet, in a moment of extraordinary cosmic coincidence, our artificial intelligence systems caught it. A single flicker of motion in the vast stillness. It was luck beyond reason, a once-in-human history alignment of algorithms, telescopes, and timing. Against every odd the universe could offer, we glimpsed a wanderer that had roamed the dark for eons. And for a fleeting moment, it let us see it. The Atlas telescope network works like a robotic sentinel, tirelessly watching the heavens for anything that dares to move. 4 observatories, stationed across Hawaii and South Africa, sweep enormous portions of the sky several times each night. Each telescope captures the same starfields again and again, comparing them to spot even the faintest flicker of motion against the endless background of fixed stars. Every night, the system processes over 100 gigabytes of data, analyzing millions of stellar positions with the help of advanced machine learning algorithms. To find 3 Atlas, the AI had to detect a single, almost imperceptible dot of light that shifted just enough between exposures to signal movement, but not so much that it blurred into a streak. It was a task that demanded precision bordering on the impossible. Because of its hyperbolic velocity, 3 Atlas swept across the sky far faster than any typical comet or asteroid, giving scientists only a tiny window of opportunity, mere days instead of months, to notice it. Miss that window, and the traveler would vanish forever into the dark beyond our solar system. The challenge wasn't just speed, it was deception. The AI had to sift through thousands of false positives every night, Cosmic rays strike the sensors, creating phantom sparks that mimic motion. Satellites and space debris carve streaks of light through the frames. Even something as mundane as a bird crossing the lens can confuse the detectors and trigger a false alert. Over years of observation, however, the system learned. Its neural networks were trained on vast archives of sky survey data until they could distinguish truth from illusion, recognizing the quiet, steady patterns of genuine celestial motion buried within oceans of noise. And then, one night, the algorithm saw it, a faint, unblinking point of light gliding across the void, moving too fast for a comet, too distant for a satellite, too consistent for a sensor glitch. Frame after frame, its position followed perfect gravitational logic. It was no artifact, no mistake, no malfunction. It was 3 Atlas, a messenger from another star system, caught for a brief moment by the watchful eyes of machines built to find the unfindable. The discovery of 3 Atlas was an act of pure astronomical luck, the kind of coincidence that might only happen once in a civilization's lifetime. By sheer chance, the object passed through a region of sky that the Atlas telescope network was already surveying that week, and under perfect conditions. Clear weather, functioning instruments, and no maintenance interruptions. A few hours of cloud cover, a single calibration delay, and humanity would have missed it forever. It would have slipped silently through our solar system, unseen and unremembered. A cosmic visitor no one ever knew had come. Once the machine learning system flagged the anomaly, an automatic global alert spread through the international network that connects observatories around the world. The Minor Planets Center in Cambridge took charge, verifying the data and calculating an initial orbit. Within hours, telescopes from Chile to Japan, from Hawaii to Spain, were all aimed at the same streak of darkness crossing the stars, tracking what was now confirmed to be an interstellar intruder. Follow-up observations quickly revealed just how extraordinary this discovery was. Ground-based telescopes measured its brightness, estimating its colossal size. Spectroscopic instruments began splitting its reflected light into wavelengths, decoding the chemical composition of its icy surface. Radio telescopes scanned for any unnatural signals, the faintest hint that this might be something more than just rock and ice, while infrared sensors measured the object's heat signature to infer its internal structure. It was a masterclass in global scientific coordination. Space agencies, research universities, and observatories all shared resources and telescope time, reworking entire observing schedules to focus on this one fleeting target. For once, humanity looked outward in perfect unison. Scientists from every continent racing to capture every photon of light 3 Atlas reflected. Before it vanished into the deep, computer models projected its trajectory and lifespan in our skies. The calculations were sobering. Only a few months of visibility before it would fade beyond detection forever. Every observation, every spectrum, every image mattered. Then came the first results, and they changed everything. When the spectroscopic data arrived from major observatories, astronomers stared in disbelief. The light signatures didn't make sense. 3 Atlas appeared to contain chemical combinations that should not exist together in nature. Elements and compounds that, by every known rule of chemistry, could not coexist in a stable body. It was as if the object were bleeding contradictions, an impossible mixture of substances that defied the laws governing the formation of planets, stars, and comets. For the first time, scientists realized they weren't just studying a visitor from another star system. They were confronting a new kind of matter, forged under conditions no human model had ever imagined. Every comet humanity has ever studied carries a familiar chemical story. A predictable balance of water vapor, carbon monoxide, and carbon dioxide that reflects the conditions in which it was born, far from the warmth of its parent star. But 3 Atlas broke that story apart. Its chemistry wasn't just unusual, it was impossible. The first spectral analyses revealed something startling. Carbon dioxide dominated everything, drowning out the usual signals of water and other volatiles. Typical comets release mostly water vapor when heated by a nearby star, forming the bright, shimmering tails that sweep across the night sky. But 3 Atlas did something no comet should do. It exhaled carbon dioxide in quantities that outnumbered water emissions by orders of magnitude, ratios so extreme that no known process of planetary formation could explain them. Spectroscopy, the method of splitting light into its component wavelengths, allows scientists to read the fingerprints of molecules across space. Each chemical compound absorbs and emits light at distinct narrow bands, leaving a unique pattern of lines that reveal its identity. When the light of 3 Atlas was spread into its spectral components, the result was unmistakable: intense, blinding signatures of carbon dioxide, so powerful they drowned nearly every other molecular feature. But the real puzzle lay in what wasn't there. The usual water vapor lines were faint, barely detectable, an anomaly unheard of for a comet passing near a star. Carbon monoxide, another common volatile that should have been abundant in a body forged in deep cosmic cold, was also mysteriously scarce. The spectrum didn't just look strange, it looked wrong. As if 3 Atlas had formed in a chemical reality different from our own. And yet, the object wasn't barren. Hidden among the data were complex carbon chains, long molecular structures that hinted at rich organic chemistry, but with ratios no human instrument had ever recorded. Even more striking were the faint ultraviolet lines indicating cyanide compounds, molecules that on Earth are associated with both toxicity and prebiotic chemistry. These signatures suggested formation, conditions utterly alien to any known stellar nursery, perhaps shaped by radiation environments or pressure gradients beyond anything our solar system could reproduce. The strangeness didn't stop there. Deeper analysis revealed isotopic anomalies, subtle variations in the ratios of atoms like carbon and oxygen that serve as fingerprints of their birthplaces. On Earth and in our local solar system, these ratios fall within narrow, well-understood ranges. But 3 Atlas bore ratios shifted far beyond those boundaries, implying that it formed in a region of the galaxy with different stellar radiation fields and elemental abundances, a corner of the Milky Way, older and more chemically primitive than our own. Professional chemists and planetary scientists scrambled to make sense of the data. Some proposed that 3 Atlas might have originated around a dying star, where extreme radiation could strip water while preserving heavier carbon molecules. Others imagined a protoplanetary disk bathed in intense ultraviolet light, creating exotic reactions that locked carbon dioxide into its core. A few dared to suggest that 3 Atlas could be a remnant of a system unlike any we've ever seen, one that obeyed a different set of chemical rules altogether. Whatever the truth, one fact was certain: 3 Atlas was not just a visitor from another star system, it was a chemical messenger from another era of the galaxy's history, carrying within its frozen heart the blueprint of a world we may never find again. Perhaps 3I Atlas was born within a stellar system utterly unlike our own, one whose metallicity defied the norm, where heavy elements formed in rare proportions under alien suns. Some researchers propose that its chemistry may have been sculpted over billions of years by interstellar radiation, exposure so ancient and so prolonged that it rewrote the surface chemistry through processes that have no parallel within our solar system. Others reach further still, imagining a birthplace beyond the familiar ice lines of a forming star, those invisible boundaries where certain gases freeze and others remain vapor. If true, then 3I Atlas may have emerged from regions so cold and distant that carbon dioxide became the dominant ice instead of water. Such a world would require a planetary architecture completely unlike our own, one where frozen carbon ruled, and water was a rarity rather than the foundation of chemistry. No laboratory on Earth can recreate the pressures, radiation fields, or epochs that shaped this object. 3I Atlas is not merely a comet, it is a relic from conditions that no longer exist. A fossil carrying the chemistry of other suns, it drifts through space as a messenger from an environment that modern science can only model in theory. Yet its carbon dioxide emissions reveal an even deeper strangeness, one that borders on the industrial. Measurements from the James Webb Space Telescope showed that 3I Atlas vents carbon dioxide at an astonishing rate of 129 kilograms per second. That's the mass of a small car every few seconds, expelled into the void in a silent, relentless stream. This immense outgassing forms an invisible envelope of gas stretching more than 200,000 meters from its core, a vaporous halo of carbon dioxide brighter and denser than any ever recorded. The ratio between carbon dioxide and water stands at 8:1, the most extreme imbalance ever observed in any comet. For comparison, ordinary comets in our solar system exhibit the opposite behavior. Their emissions are dominated by water vapor, often in ratios of 10:1 against carbon dioxide. 3I Atlas reverses this relationship completely, as though its chemistry had been inverted at birth. Such an anomaly does more than challenge our understanding. It undermines the very foundations of cometary science. It suggests that the rules governing how ices condense in protoplanetary disks might vary dramatically across the galaxy. It hints at worlds built from unfamiliar recipes, where carbon outnumbers oxygen, and where the very notion of habitable chemistry might mean something entirely different. To comprehend this, scientists turn to the physics of activation, the moment when sunlight awakens a frozen traveler. As 3I Atlas nears a star, solar radiation seeps into its ancient crust, heating the buried ices until they leap directly from solid to gas, bypassing any liquid phase. The process resembles dry ice evaporating on Earth, but magnified to geological proportions. A cosmic respiration that persists for months as the comet races along its hyperbolic path through our solar system. Each molecule of carbon dioxide that escapes carries with it the fingerprint of a system long dead, an echo of chemistry forged under alien skies. In that invisible plume, 3I Atlas tells the story of a universe still inventing ways to surprise us. The energy balance within 3I Atlas reveals contradictions that defy our expectations of cometary physics. Normally, carbon dioxide sublimates at higher temperatures than water ice, meaning it should awaken later, only after a comet draws close to its parent star. Yet 3I Atlas breaks this rule completely. It releases torrents of carbon dioxide while its water emissions remain faint and reluctant, as if the comet's chemistry operates on alien logic. This imbalance hints at an extraordinary surface composition or an interior unlike any other known comet. One theory suggests a process called preferential sublimation, a phenomenon where surface layers rich in carbon dioxide ice sublimate first, forming a crust that seals off the water ice below. Imagine 3I Atlas cloaked in a carbon dioxide shell, built slowly over billions of years as it drifted through the interstellar deep. Beneath that crust, the water ice lies trapped, unreachable by sunlight, preserved like a frozen memory from another system. Other researchers propose an even stranger possibility, that 3I Atlas never contained much water to begin with. Perhaps it formed in a young stellar system where the balance of elements was inverted, a world where carbon dioxide was abundant and water was rare. Such systems might orbit stars of unusual metallicity, where heavy elements and radiation sculpt chemical environments far removed from the template of our solar system. In these alien nurseries, the so-called ice lines would be rearranged, and carbon-rich frost would dominate regions where Earth's builders once found water. But the mystery deepens when examining how 3I Atlas maintains its prodigious gas output. For a comet to vent such volumes, its interior must allow heat and vapor to move freely. Computer models paint a picture of a porous nucleus, a fragile matrix of cavities, fissures, and microscopic tunnels threading through the rock and ice. As sunlight strikes the surface, it seeps inward, heating deeper layers and triggering hidden reservoirs to awaken. Through these labyrinthine pathways, gases percolate upward, escaping into space in great invisible streams. It is as if the comet breathes, inhaling starlight, exhaling alien chemistry. The structure itself acts like a cosmic lung, expanding and contracting as energy flows through it. Each plume of escaping vapor tells us that 3I Atlas is not a solid monolith, but a living relic of frozen voids and fractured channels, a body built by time, radiation, and silence. Its porous interior, its uneven composition, its premature awakening, all whisper of an origin story beyond the patterns we know, written in the languages of other stars. Spacecraft missions to comets within our solar system have revealed that these ancient bodies are far from uniform. They are layered worlds, composed of stacked and tangled histories. Beneath dusty crusts lie strata of ice, rock, and frozen gases, each formed under different cosmic conditions. 3I Atlas may represent the most extreme version of this architecture yet observed. Its structure appears to contain carbon dioxide-dominated zones isolated from deeper, water-rich regions by impermeable barriers, frozen walls that prevent the normal blending of volatile materials during sublimation. This strange internal arrangement has visible consequences. The comet's immense carbon dioxide cloud, an expanding invisible shroud that extends hundreds of kilometers into space, offers both an opportunity and a complication for astronomers. Infrared observatories can pierce the veil to map its three-dimensional shape, tracing temperature gradients, gas flows, and faint turbulence patterns that reveal how sunlight stirs its alien atmosphere. Yet that same cloud hides the comet's heart. The true nucleus of 3I Atlas, where these reactions originate, remains cloaked behind a fog of its own creation. But within that fog lies a discovery that defies every established model of cosmic chemistry. Instruments at the Very Large Telescope in Chile detected metallic nickel vapor in the comet's spectrum without any corresponding trace of iron. That single absence transforms an observation into a mystery. Nickel and iron are cosmological twins, born side by side in the fiery furnaces of dying stars. Every known planet, meteorite, and comet in the universe contains both in nearly fixed proportions, defined by the physics of nucleosynthesis. Yet 3I Atlas breaks that rule. Its emission lines reveal pure nickel vapor, bright, unmistakable green signatures produced when solar radiation excites nickel atoms, causing them to glow at precise quantum wavelengths. No hint of iron accompanies them. The detection itself required extraordinary precision. Nickel emissions are vanishingly faint, often drowned in the glare of a comet's dust and gas. Only the most sensitive spectrographs, operating with hours-long exposures, could isolate such a signal. And yet, observation after observation confirmed it. Independent teams across multiple nights saw the same spectral fingerprint, nickel shining alone in the interstellar dark. On Earth, nickel and iron are inseparable companions, blended in meteorites, alloyed in planetary cores, forged together in stars. Their consistent ratio forms a cosmic constant, a chemical signature of stellar birth and planetary evolution. To find nickel unaccompanied by iron is to encounter an object that should not exist under the known laws of stellar chemistry. Atlas, it seems, carries within it the residue of a world built from unfamiliar matter, a fragment of a system whose elemental balance diverged fundamentally from our own. Its metallic breath challenges our models of how atoms assemble, how stars enrich their planets, and how the periodic table itself unfolds across the galaxy. Atlas breaks the cosmic patterns so completely that its very chemistry suggests formation processes, or later transformations, that lie beyond anything current science can explain. Even stranger, the nickel emissions it produces are not steady. Over the course of only a few weeks in mid-2025, their intensity surged by nearly 25 times, following a precise mathematical progression that implies something systematic happening deep within the comet's structure or on its evolving surface. Such behavior is unprecedented. In laboratory conditions on Earth, the separation of nickel from iron requires highly controlled environments, industrial furnaces, electrochemical baths, or specialized metallurgical systems operating at extreme temperatures. Nature has no known counterpart for such processes. Yet 3I Atlas somehow achieves them in the vacuum of space, under sunlight alone. Some planetary scientists have proposed a more restrained possibility. Perhaps the comet's surface contains nickel-rich minerals that vaporize more easily than their iron-bearing counterparts. As solar radiation heats its crust, these compounds could sublimate first, releasing nickel gas while iron remains trapped in more resilient, deeper layers. But this explanation falters under scrutiny. No mineral known to science exhibits the degree of separation observed in 3I Atlas. The ratio is too extreme, the distinction too absolute. Others have looked farther back, into the birthplaces of stars themselves. Maybe 3I Atlas was forged in a system whose physical laws unfolded differently. A stellar nursery shaped by intense magnetic fields, or radiation spectra capable of sorting elements in ways our own solar nebula never could. Such conditions could, in theory, create a material inheritance alien to everything found in local space. And then comes the hypothesis few scientists voice openly, but none can ignore. Artificial processing. Industrial extraction of nickel from iron on Earth produces chemical byproducts that, if incorporated into a larger structure, might one day drift through space carrying a signature of deliberate refinement. The spectral purity of 3I Atlas, the clean, isolated fingerprint of nickel without iron, resembles such a byproduct more than any natural ore. The notion that it might be debris from an ancient civilization, a shard of technology eroded by eons, remains wildly speculative, but no longer entirely unthinkable. Regardless of origin, The object itself is ancient beyond comprehension. Computer simulations tracing its path backward through the Milky Way suggest that 3I Atlas has been traveling the interstellar medium for between 7 and 14 billion years, older, potentially, than many of the galaxy's stars. For perspective, our entire solar system is a recent arrival at only 4.6 billion years old. This means 3I Atlas may have been flung from its parent world when the universe was still young, when galaxies were fewer and the first heavy elements were just beginning to seed the cosmic dust. That it has survived this long is a marvel of endurance. Interstellar space is not empty. It is a storm of invisible violence, high-energy cosmic rays, accelerated by supernovae and black hole jets, constantly pummel wandering objects, stripping surfaces, fracturing crystals, and eroding smaller bodies into vapor. Most comets disintegrate after only millions of years. Yet 3I Atlas has endured for billions, carrying within its fractured heart the chemical record of a vanished system, and perhaps the trace of something once made, rather than merely born. These high-energy particles penetrate the outermost layers of any object they strike, shattering chemical bonds and rewriting the molecular architecture atom by atom over immense spans of time. The radiation field between stars is vastly more hostile than anything within a solar system. Out here, their 3I Atlas, however, is far larger than this survival threshold, massive enough to preserve a deep interior untouched by the violence that scoured its surface. Over time, its outer layers must have transformed into what planetary scientists call a radiation-processed crust, a hardened skin forged by endless impacts of high-energy particles. Each collision split molecules apart, reassembled them into strange new compounds, and slowly altered the spectral fingerprint of the surface. This shell became both scar and shield, absorbing the punishment of interstellar travel while sealing away the ancient chemistry beneath. Laboratory experiments using particle accelerators can only hint at what such cosmic exposure accomplishes. Even under accelerated bombardment, organic molecules disintegrate or simplify in mere years, yet 3I Atlas still carries traces of complex carbon chains, structures that should not have survived. This implies one of two possibilities. Either it formed with extraordinarily resilient organics never before seen, or some unknown self-preserving mechanism protected its chemistry through eons of exposure. Inside, the temperatures would have fallen near absolute zero, around -400 degrees Fahrenheit, so cold that motion itself nearly stops. At such extremes, chemical reactions freeze into dormancy, preserving compounds as they were when the universe was young. Every molecule locked within the comet's heart became a relic, a physical memory of the conditions under which it was born. In essence, 3I Atlas is a cosmic fossil, a survivor of epochs when galaxies were still assembling, and starlight had only just begun to illuminate the dark. Its radiation-sculpted crust and frozen core hold within them the story of matter's endurance, the quiet defiance of chemistry that refused to decay even under the universe's most relentless assault. Helping preserve the original chemistry forged billions of years ago within its parent stellar system, this tiny traveler became a frozen time capsule, a messenger carrying untouched fragments of planetary birth. Over eons, its path was reshaped by the gravity of wandering stars, tugged and redirected countless times as it drifted through the interstellar dark. Simulations reveal that such long-lived voyagers often cross through many stellar neighborhoods, their courses twisted by invisible hands of gravity, their speed subtly rewritten by each encounter. Yet somehow 3I Atlas endured, never captured, never shattered, surviving the chaos of cosmic tides that should have torn it apart. The thin layer of material scorched and processed by radiation on its surface tells part of its story. Spectroscopic readings only reach this outermost skin, suggesting that the strange chemistry we see today may not reflect its birth, but rather billions of years of exposure to cosmic rays, the slow carving of eternity into its crust. Beneath that ancient shell, deeper layers might still hold the original essence, matter untouched since the dawn of its creation, mirroring the familiar materials of our own solar system. But the true wonder lies in its birthplace, the turbulent heart of our galaxy's youth. 3I Atlas carries within it the chemical whispers of cosmic dawn, formed in a time when the Milky Way was violent and new, when the first generations of stars exploded and seeded the void with the raw ingredients of worlds yet unborn. astronomers retrace the journey of 3I Atlas backward through space and time, running complex computer simulations that map the gravitational pull of billions of stars across millions of years. The data points toward a striking origin: the Milky Way's thick disk, a vast population of ancient stars born when our galaxy was young, turbulent, and forming stars at a furious pace nearly 10 billion years ago. This thick disk stands as a fossilized record of that chaotic youth, an age when colossal stellar explosions filled space with the first heavy elements, seeding the cosmos with the ingredients of worlds to come. The stars born then bear chemical marks unlike our suns. Fewer metals, fewer traces of anything beyond hydrogen and helium. And within 3I Atlas, those same fingerprints remain, preserved across eons like a coded memory of galactic childhood. To understand its meaning, astronomers divide the Milky Way into distinct layers of history. The thin disk, home to our solar system, is filled with younger stars rich in heavy elements, the recycled ashes of countless stellar generations. But the thick disk is older, quieter, more primordial, a population forged before the galaxy fully matured, when enrichment had barely begun. Chemical. Studies of 3I Atlas reveal a metallicity, the abundance, of elements heavier than hydrogen and helium, around 40% that of the Sun. This perfectly matches the thick disk population. Even its motion through space supports the same conclusion. Objects expelled from stellar systems carry the momentum of their parent stars, and 3I Atlas travels in a way characteristic of thick disk orbits, long, elliptical paths that lift far above and below the galactic plane, unlike the smoother motions of younger, thinner disk stars. If 3I Atlas was indeed born in that ancient environment, its entire existence unfolded under alien conditions. The dense stellar regions of the thick disk would have increased gravitational interactions, making it easier for comets and asteroids to be flung free from their home systems. Massive nearby stars would have bathed the region in fierce radiation and stellar winds, reshaping the chemistry of newborn planetary disks. The result is an object like no other, forged in a time of chaos, altered by extremes, and cast adrift into interstellar space, carrying within it the rare chemical echoes of a galaxy still learning how to build itself. In regions of low metallicity, where heavy elements are scarce, the building blocks of worlds form in unfamiliar ways. Protoplanetary disks born around such ancient stars would have possessed very different ice lines, the invisible boundaries where gases like water, methane, and carbon dioxide condense into solid form. In these environments, carbon dioxide may have been far more abundant than water ice, a chemical balance shaped by the primitive radiation, fields and elemental makeup that existed long before the Sun was born. Studies of thick disk stars reveal that they emerged during one of the Milky Way's most violent eras, a time when our young galaxy was colliding and merging with smaller companions. These galactic mergers triggered intense bursts of star formation, unleashing gravitational chaos that could have easily cast newborn asteroids and comets out into interstellar space. 3I Atlas may be one such relic. Debris born from planetary systems forged amid the cosmic upheaval of early galactic history. By dating the thick disk population, astronomers place the origin of 3I Atlas in an age known as cosmic noon, roughly 2 to 3 billion years after the Big Bang. It was a time when the universe burned brightest with creation. When star formation peaked, galaxies matured rapidly, and the first significant amounts of heavy elements began to weave themselves into planets, moons, and comets. Yet the mystery deepens. 3I Atlas is no fragile wanderer. It is an interstellar giant, nearly 10 million times more massive than any previous visitor we've detected between the stars. Its existence strains probability itself, hinting that the cosmos may be far richer in these titanic drifters than we ever imagined. This single object, drifting silently through the dark, forces astronomers to confront a profound question. If something this immense could have formed and survived from the dawn of galaxies, how many more ancient travelers might still be crossing the endless spaces between worlds, unnoticed, waiting to be found? With a nucleus nearly 7 kilometers wide, 3I Atlas possesses an estimated mass of around 1 trillion kilograms, assuming a density similar to ordinary cometary ice and rock. That makes it a cosmic heavyweight, rivaling some of the largest asteroids in our solar system. yet hurtling through space at velocities far exceeding anything gravitationally bound to the Sun. When compared to its interstellar predecessors, the scale of 3I Atlas becomes almost unimaginable. Oumuamua, the first confirmed interstellar visitor, measured roughly 400 meters in length and weighed perhaps 10 million kilograms. Borisov, the first known interstellar comet, stretched about 1 kilometer across with a mass near 1 billion kilograms. 3I Atlas surpasses both by staggering factors. A leap so vast, it challenges every statistical model of how such objects should exist. Astronomers know that cosmic debris follows a power law distribution. Smaller bodies vastly outnumber large ones, typically by a factor of 10 for each tenfold decrease in size. By that logic, detecting an object as massive as 3I Atlas so early in our brief catalogue of interstellar discoveries seems statistically impossible. To find one so soon, before millions of smaller wanderers had been seen, suggests that something fundamental is missing in our understanding of how material is ejected from distant planetary systems. Perhaps our assumptions are flawed. Maybe giant planets, far larger than those in our solar system, can hurl out massive objects with surprising efficiency, shaping population distributions in ways we've never observed. Or perhaps our detection methods simply favor the largest travelers, whose brightness and outgassing make them visible across far greater distances, giving us a skewed view of what truly roams between the stars. Yet the mystery runs deeper. The sheer energy required to eject something as massive as 3I Atlas defies ordinary planetary mechanics. Simulations show that only encounters with super-Jupiter worlds, or even more extreme gravitational systems, could provide the necessary slingshot. Velocity. Some theorists suggest binary star systems as the solution, twin suns locked in orbital dance, their combined gravity producing rare resonant interactions, capable of flinging colossal bodies into interstellar darkness. During precise alignments, these systems could generate the immense energy needed to expel an object like 3I Atlas. But such circumstances demand near-perfect tuning, a cosmic choreography unlikely to occur often, and so 3I Atlas remains a paradox, a trillion-ton messenger from another star, moving impossibly fast, born of conditions that seem almost too rare to exist. Its discovery hints that the galaxy may hold far stranger architectures than we ever imagined, and that the mechanisms shaping interstellar space are not only more violent, but also more creative than our models dare to predict. The very survival of 3I Atlas over billions of years in interstellar space is itself a marvel of scale and endurance. Its sheer size may have been its greatest shield. Smaller wanderers, with far higher surface-to-volume ratios, succumb quickly to the slow erosion of cosmic rays and the relentless abrasion of interstellar dust. But 3I Atlas retained enough mass to preserve its internal chemistry and structure, weathering a radiation environment that would have long since obliterated lesser travelers. Modern surveys for interstellar objects further emphasize this bias. Our telescopes can only glimpse the large, bright ones that reflect sunlight strongly enough to betray their passage. It's entirely possible that 3I Atlas is merely the visible crest of a vast hidden population. Countless dim, cold fragments drifting invisibly between the stars, too small or too dark for detection. And yet, even among such mysteries, the most perplexing feature of 3I Atlas is not its mass, but its trajectory. Its orbit through our solar system aligns with such impossible precision that chance alone cannot explain it. The object travels at an inclination of just 5 degrees from the ecliptic plane, the same flat disk where Earth, Mars, Jupiter and Saturn all trace their paths around the Sun. Statistically, that alignment borders on the absurd. If interstellar visitors truly arrive from random directions, their paths should scatter evenly across every possible angle, forming a uniform shell of approach points around the solar system. In that model, an object aligning this perfectly with the planetary plane should occur less than 0.2% of the time, a probability so small it defies coincidence. To grasp how strange this is, imagine space as a great three-dimensional sphere encompassing our solar system. Random objects could approach from any point on that sphere, above, below, or far askew from the narrow strip of orbits where our planets move. Yet 3I Atlas entered almost flush with that delicate plane, slipping among the paths of worlds, as if following a route already known. The deeper the orbital analysis goes, the more improbable the coincidence becomes. Beyond mere inclination, Factors like perihelion distance, velocity vector, and node alignment compound the improbability, forming a web of parameters so finely tuned that they appear orchestrated. Whether this precision arose from the chaos of galactic dynamics or from some still hidden gravitational influence, 3I Atlas moves as though it remembers the map of our solar system, a frozen relic from another star that somehow found the one path where mathematics itself begins to falter. 3 Atlas moves toward our Sun in retrograde motion, traveling backward against the direction of the planet's orbit. Retrograde trajectories are not entirely unexpected among interstellar visitors, but when this motion combines with the comet's low orbital inclination, the odds of such alignment arising by chance collapse to nearly zero. Professional astronomers and statisticians have analyzed every element of its motion: approach angle, velocity, inclination, direction of travel, and even the timing of discovery. To quantify the improbability, the results are staggering. When all these parameters are combined, the likelihood of such an object appearing by random chance is estimated to be less than once in several thousand interstellar encounters. Then comes the timing, an equally baffling coincidence. 3 Atlas was spotted precisely at the moment when it was both close enough and bright enough for extended observation, offering scientists months to study it before it faded into darkness. Statistically, such perfect timing should occur rarely, since random detections ought to distribute evenly across an object's brief window of visibility. Yet 3 Atlas appeared exactly when human technology was ready to capture it in extraordinary detail. Some researchers have proposed anthropic selection effects, the idea that objects with properties similar to 3 Atlas are simply easier to detect, giving the illusion that they are more common than they are. But even when accounting for observational bias, the probabilities still fall short by orders of magnitude. Others have suggested more exotic possibilities, gravitational, focusing effects that could bend interstellar trajectories towards specific orbital orientations. Over billions of years, the galaxy's gravitational field can indeed warp the paths of drifting objects. Yet detailed simulations reveal these forces to be far too weak to account for the razor-sharp precision of 3 Atlas's current path. The next idea is more intriguing. Perhaps 3 Atlas is not random at all. It may have been ejected from a stellar system geometrically aligned with our own, a neighboring star sharing our galactic motion, whose debris naturally follows similar orbital inclinations. In this case, 3 Atlas would not be a chance intruder, but a messenger from a parallel galactic stream, moving in quiet synchrony with our solar system across the Milky Way, and the discovery sequence itself deepens the mystery. Humanity has observed the skies for centuries, yet within just 1 decade, astronomers have detected 3 confirmed interstellar objects, a rate of discovery that implies either astonishing luck or a dramatic change in how common such wanderers truly are. But even the strange orbit, the perfect timing, and the improbabilities pale beside what came next. When the James Webb Space Telescope turned its mirrors toward 3 Atlas in August 2025, astronomers expected to find nothing more than an improved view of its carbon dioxide coma and trace minerals. Instead, Webb revealed chemistry that should not exist, molecular fingerprints that violate everything we understand about how matter behaves in the cold vacuum between the stars. Operating in the infrared, Webb can see what ground-based telescopes cannot. It peers through gas and dust to expose the hidden architecture of molecules. What it found in 3 Atlas would soon send ripples through every corner of astrophysics, forcing scientists to ask whether this object was simply ancient or something the universe itself was never meant to make. Its vast 18-segment primary mirror, larger than a tennis court when fully unfolded, gathers enough light to decode the chemical fingerprints of worlds billions of miles away with stunning precision. Using this power, Webb's near-infrared spectrograph mapped the molecular landscape across the coma of 3I Atlas, revealing how gases swirl and distribute around its mysterious nucleus. What the telescope saw defied every expectation. Carbon dioxide appeared 8 times more abundant than water vapor, an inversion of what's typical for comets. And Webb's 3-dimensional data showed that the gas wasn't spread evenly. Instead, carbon dioxide clustered in distinct regions, hinting that Atlas's surface might be a mosaic of exotic ices or that its internal structure channels gas through hidden vents like breath escaping from a fractured lung of stone and ice. Webb's instruments also detected a chemical complexity unlike anything seen before. Carbon chain compounds, nitrogen-bearing nitriles, and long organic polymers emerged in abundance, suggesting the comet was shaped or altered under conditions utterly foreign to our solar neighborhood. Then came the most shocking revelation: the isotopes. Webb's sensitivity allowed scientists to measure rare isotopic fingerprints of carbon, nitrogen, and oxygen, each acting as a time capsule from the comet's birthplace. These ratios didn't match anything from our sun, our planets, or even the familiar interstellar medium. Such chemical signatures point to an origin around a star unlike our own. Perhaps one with a different mass, metallicity, or life cycle, where nuclear processes forged matter under alien rules. 3I Atlas may have been born in the disk of a long-dead sun, carrying in its frozen heart the record of another star's chemistry, another galaxy's memory, and another era of creation entirely. Webb's data also revealed something no one expected. The comet's chemistry was changing with time, and not in any predictable way. Most comets, as they drift closer to their stars, release gases in a smooth, gradual rhythm, their frozen cores breathing out in steady cycles of heat and light. But 3I Atlas broke every rule. Its chemical emissions surged and dipped erratically, each molecule seeming to follow its own mysterious pulse. Temperature maps from Webb showed another impossibility. The comet's surface was warm enough to sublimate carbon dioxide efficiently, yet somehow kept its water ice locked solid, never melting away. This strange duality suggested a bizarre surface structure, perhaps layered, porous, or shielded, that allowed carbon dioxide to escape while trapping water beneath an insulating crust. And then came the silences, the missing chemicals. Webb's exquisitely sensitive instruments detected no methane, no ammonia, no hydrogen sulfide, all of which are normally abundant in comets born within solar systems. Their absence painted a picture of a body formed under alien chemical laws, far from any environment we've known. But the most bewildering clue came next, the metal that shouldn't have been there. 3I Atlas emitted a vapor of pure nickel. Not nickel alloyed with iron, not embedded in minerals, atomic nickel, glowing in space. Ground-based telescopes scrambled to confirm it. The Very Large Telescope in Chile, using its adaptive optics to pierce through Earth's atmosphere, locked onto the comet's faint spectral fingerprint, a bright green emission line at 527.03 nanometers, the unmistakable signature of nickel atoms excited by sunlight. The signal wasn't a glitch. It was strong, real, and consistent. Even more astonishing, the intensity of that nickel glow increased 25-fold. Atlas wasn't entirely natural. What if, buried within its alien ice and nickel skin, there lay evidence of an origin more deliberate? Something built, not born. What made the mystery even deeper was not just what was found in the spectrum of 3I Atlas, but what wasn't. The comet's bright nickel signature appeared alone, with no trace of iron anywhere beside it. In the known universe, that simply doesn't happen. Nickel and iron are cosmic twins, forged together in the furnaces of dying stars, their ratios fixed by the nuclear reactions of stellar evolution. Wherever one is found, the other follows. Yet 3I Atlas broke this law of nature. Its isolation of nickel created a chemical fingerprint unseen in any natural environment. On Earth, separating nickel from iron requires intense, industrial-scale refinement, smelting, electrolysis, or precision metallurgical processes powered by immense energy. Such separation demands purpose, technology, and control. Nothing in the raw chemistry of space should be capable of achieving it. Some scientists scrambled for explanations. Perhaps 3I Atlas carried rare nickel-rich minerals that vaporized more readily than their iron-bound counterparts. Maybe it formed in a system with magnetic fields so intense they altered how metals condensed and sublimated. Others speculated about photochemical effects from an exotic star that might have stripped nickel and iron apart through radiation over eons. But none of those models worked. No known mineral structure or thermodynamic process can account for the extreme fractionation observed. The data simply refused to fit within the boundaries of natural chemistry. Then came the temporal clue. The nickel signal itself wasn't static. It increased 25-fold in intensity, following a mathematical rhythm too precise to be random. The pattern looked more like a controlled process than a natural flare. more algorithmic than geological. Harvard astrophysicist Avi Loeb pointed out that, on their own, any one of these anomalies, the nickel-only emissions, the low inclination orbit, the improbable timing, might be dismissed as coincidence, but taken together, they defied probability. His conclusion was careful but chilling. Perhaps 3I Atlas isn't a comet at all. Perhaps it's a piece of technology, ancient, derelict, or deliberate, crossing the void under laws of creation not our own. These speculative theories soon drew the attention of the world's leading space agencies, organizations now compelled to step out of silence and confront a wave of public fascination that bordered on obsession. Across social media and astronomy forums, whispers grew into global debate. Was 3I Atlas merely an interstellar comet, or something else entirely? Its impossible orbit, its alien chemistry, its defiance of statistical logic. Each new detail fueled the belief that this object might not be natural at all. Harvard astrophysicist Avi Loeb, known for his bold hypotheses about Oumuamua, once again entered the spotlight. His detailed analysis concluded that 3I Atlas displayed several anomalies inconsistent with natural objects: a precise orbital alignment, the absence of iron where it should exist, and a timing of discovery that seemed almost engineered. On Loeb's artificial likelihood scale, the object scored a 4 out of 10, not confirmation of alien technology, but enough to ignite public imagination. Within days, the speculation outpaced science. Hashtags and amateur theories filled digital spaces faster than researchers could respond. The tension pushed NASA, the European Space Agency, and other astronomical institutions to issue formal statements, an increasingly rare step meant to steady public perception before fiction overtook fact. NASA's response was cautious but firm. They reminded the world that strange does not mean unnatural. Cometary nuclei, they explained, can evolve over billions of years in deep interstellar space, enduring radiation, impacts, and chemical transformation. Such extreme aging can produce compositions utterly unlike anything born within our solar system. No alien intent was required, only time and physics. The agency addressed the mysterious nickel without iron emissions directly. Scientists proposed that selective sublimation, the process by which certain metals vaporize more readily under solar heating, might naturally separate nickel from iron in rare mineral structures. Laboratory meteorite samples, they noted, have shown fragments of such phases, though seldom in such purity. As for 3I Atlas's improbable orbit, officials pointed toward detection bias. Our telescopes, they explained, are far more likely to spot objects that approach within certain angles or reflectivity thresholds. What appears aligned by design could simply be the illusion of probability shaped by human observation limits. And yet, despite the reassurance, one truth lingered in the air. Official explanations could only describe what might be, not what was. The silence between the facts left room for imagination to grow. The apparent statistical oddities surrounding 3I Atlas, scientists cautioned, may not defy probability at all. They may simply mirror the biases of how we observe the sky. Astronomers reminded the public that nature often appears extraordinary only until our understanding catches up. Selection effects, instrumental limitations, and the geometry of observation can all make rare events seem miraculous when they are merely misunderstood. Professional researchers emphasized a crucial point. Science does not begin with the extraordinary. It earns its way there. Every anomaly, no matter how strange, must first be tested against the full range of known physical explanations before speculation takes hold. As debate raged online, observatories worldwide continued gathering data, and the emerging picture began to align with something more familiar. Multiple research teams independently confirmed that 3I Atlas behaves, fundamentally, like a comet. Its dust jets, gas release, and expanding coma followed thermal models consistent with the sun's radiation acting on volatile materials. Infrared readings traced surface temperatures and spectra matching rocky, icy compositions. Photometric analysis revealed reflectivity patterns indistinguishable from known comet nuclei. Even radio telescopes scanning for any trace of artificial transmissions found nothing. No directed signals, no modulated frequencies, only the soft hum of natural radiation and sunlight scattered from its drifting surface. The SETI Institute, Running synchronized monitoring campaigns across multiple frequency bands confirmed these results. Whatever mysteries surrounded 3I Atlas, there was no evidence, none, that it was transmitting, maneuvering, or behaving like technology. A scientific consensus began to crystallize. 3I Atlas, they concluded, was extraordinary, not because it was artificial, but because it was ancient, an authentic interstellar comet forged in conditions unlike any our solar system had ever known. Its chemistry, its orbit, even its improbable composition, all testified to the immense diversity of planetary formation across the galaxy. What once seemed impossible might simply reflect how little humanity has sampled the cosmos. And yet, even as certainty grew, the story took a bittersweet turn. The object was now racing toward the defining moment of its journey, its perihelion passage, the closest point to our Sun. Astronomers calculated that on October 30th, 2025, 3I Atlas would reach a distance of 1.36 astronomical units, passing between Earth and Mars, closer than any interstellar visitor ever recorded. But fate, as often in astronomy, dealt a cruel alignment. During this brief, fiery encounter, 3I Atlas would vanish completely behind the Sun, from Earth's perspective, lost in the blinding glare of solar conjunction. Even the most advanced telescopes would be rendered useless, unable to pierce the brilliance that would swallow the comet's reflection. For scientists, it was a cosmic tragedy. The most critical and dynamic phase of this billion-year wanderer's life would unfold unseen. Models predicted that as it swept through its closest approach, solar heating would surge, driving carbon dioxide emissions from their current 129 kilograms per second to several times that rate. Its tail would likely bloom into a luminous, volatile arc, a spectacle of vapor, dust, and light. But humanity would not witness it. At the height of its transformation, 3I Atlas would pass unseen, its secrets burned into silence on the far side of the Sun. Surface temperatures may rise high enough to vaporize the buried layers of water ice beneath the comet's carbon dioxide-rich crust. Computer simulations predict that this intense perihelion heating could trigger structural shifts deep inside the nucleus of 3I Atlas, as pressure from escaping gases fractures the core and drives explosive outgassing. Many comets experience similar fates, fragmenting as internal heat overcomes their weak gravitational bonds, splitting into smaller pieces that expose fresh ice and multiply their active surface area. As 3I Atlas swings toward the Sun, radiation pressure and solar wind will sweep gas and dust outward, forming luminous tails that could stretch millions of kilometers into space. Because of its unusual retrograde orbit, these tails may twist and flow in directions rarely seen among comets of our system. Earth-based observatories have planned coordinated campaigns in September and November, hoping to study the object before and after its hidden perihelion passage. By measuring changes in gas output, dust flow, and chemical fingerprints, astronomers can infer how its interior reacts to solar heating and what this alien nucleus is made of. However, solar conjunction poses a formidable obstacle. No Earth telescope can observe a target so close to the blinding Sun. Even space observatories like Hubble and the James Webb must turn away to shield their instruments from direct sunlight. Radio telescopes might still trace its faint thermal emissions at wavelengths where the Sun's glare weakens, but such data cannot reveal the chemical richness or structure that optical and infrared eyes provide. The timing is a cruel stroke of cosmic luck. Encounters with interstellar objects of this scale may happen only once in many generations, making this lost opportunity especially bitter for astronomers. Yet hope remains beyond Earth's orbit. Spacecraft scattered across the solar system, orbiting Mars, in particular, will capture the only close-up glimpses of 3I Atlas during its most active and volatile stage. The Mars Reconnaissance Orbiter, ESA's Mars Express, and the ExoMars Trace Gas Orbiter occupy nearly perfect vantage points for October's passage. Their instruments may achieve up to 3 times the resolution of Hubble's images, revealing surface jets, fragmentation events, and evolving tails in extraordinary detail. On October 3rd, Mars aligns in opposition to 3I Atlas, just as the comet sweeps within 47 million kilometers of the red planet, offering humanity a rare, perhaps once in a century, window into the restless heart of an interstellar wanderer. This close approach places 3I Atlas nearer to Mars than it will ever come to Earth, creating unparalleled opportunities for high-resolution imaging and detailed spectroscopic analysis. The Mars Reconnaissance Orbiter carries its high-resolution imaging science experiment camera, capable of resolving surface features smaller than 1 meter on Mars. When trained on Three-Eyed Atlas, this instrument could detect structural details of the nucleus and map the three-dimensional distribution of gas and dust in the coma with precision impossible from Earth-based telescopes. Europe's Mars Express contributes complementary capabilities with its visual and infrared mineralogical mapping spectrometer, designed to identify specific minerals and chemical compounds. This instrument can detect water, carbon dioxide, and organic molecules on the comet, providing critical insight into its formation environment. Meanwhile, the ExoMars Trace Gas Orbiter, built for ultra-sensitive atmospheric chemistry studies, can measure molecular concentrations at parts per billion levels, potentially revealing minor species that Earth-based telescopes cannot detect. Coordinated observations from all three orbiters create stereoscopic imaging opportunities, allowing scientists to reconstruct the three-dimensional structure and motion within the comet's coma. By comparing simultaneous images from multiple viewing angles, researchers can map gas flows, dust particle trajectories, and internal structures that remain invisible from a single perspective. Surface-based rovers, including Perseverance and Curiosity, may also detect atmospheric changes as dust and gas from the comet interact with Mars's thin atmosphere. Their sensitive instruments could measure trace contamination from the interstellar visitor, offering ground truth data on chemical composition and particle size distributions. Observing Three-Eyed Atlas from orbit comes with unique challenges. Mars orbiters must maintain extremely precise pointing while traveling at orbital speeds exceeding 3 kilometers per second, tracking the rapidly moving comet against the stellar background. Observations also coincide with Mars's dust storm season, which can obscure surface-based measurements, though orbital vantage points place the spacecraft above most atmospheric effects, ensuring clear, uninterrupted views of the interstellar visitor. Data transmission from Mars to Earth requires careful scheduling to navigate the challenges posed by solar conjunction, which can interfere with communications to all interplanetary spacecraft. Mars orbiters must store their high-resolution images and spectroscopic data on board until reliable downlink windows become available, ensuring that the unprecedented observations of Three-Eyed Atlas reach Earth intact. These measurements capture the comet during a critical phase, carrying pristine materials from the cosmic noon epoch, when star formation across the universe reached its peak and the first heavy elements emerged. Cosmic noon occurred roughly 2 to 3 billion years after the Big Bang, marking a period when galaxies formed stars at rates 10 times higher than present-day levels, and the universe underwent its most dramatic chemical evolution. During this time, the earliest generations of massive stars lived fast and died young, exploding as supernovae and scattering heavy elements, carbon, oxygen, silicon, iron, throughout interstellar space. These elements became building blocks for subsequent stars and planetary systems. Three-Eyed Atlas formed during or shortly after this epoch, making it a direct sample of materials processed during one of the most dynamic periods in cosmic history. Spectroscopic analysis of the comet reveals chemical signatures reflecting a universe younger, more active, and chemically distinct from today's cosmos. Metallicity measurements indicate heavy element abundances consistent with stars formed during cosmic noon, higher than the earliest stellar generations, but still below solar values. This positions Three-Eyed Atlas as a relic of a transitional period when galactic chemical enrichment progressed rapidly, shaping the environments where complex chemistry and planetary systems could emerge. Star formation rates during cosmic noon exceeded current galactic activity by factors of 10 to 100, creating extreme conditions where stellar feedback, radiation, winds, and supernova operated far more intensely than today. The materials preserved within Three-Eyed Atlas offer a rare glimpse into these formative processes, enabling scientists to study firsthand the chemical evolution that shaped the universe billions of years before the emergence of our solar system. Higher supernova rates, frequent stellar collisions, and intense radiation fields from massive stellar clusters created chemical processing environments that have no counterpart in today's galaxy. Three-Eyed Atlas likely originated from the thick disk stellar population formed during cosmic noon, a period shaped by processes that remain only partially understood. Galaxy mergers, inflows of intergalactic gas, and gravitational instabilities in early galactic disks triggered bursts of star formation, establishing the chemical and kinematic signatures seen in thick disk stars. Today, protoplanetary disks forming in this epoch experienced physical conditions radically different from those surrounding present-day stars. Elevated background radiation, altered dust grain compositions, and shifted ice line locations could produce planetary systems with chemical architectures entirely unlike those in our local galactic neighborhood. Three-eyed Atlas may preserve materials formed under these exotic conditions, with isotopic ratios encoding the nuclear processes that occurred within the stellar interiors of cosmic noon. Massive stars dominated the stellar populations of the era, living short but explosive lives that enriched interstellar space with heavy elements through rapid supernova cycles. Laboratory experiments cannot replicate the immense scales of energy, time, and gravitational influence involved in these early galactic processes. Three-eyed Atlas provides direct access to these primordial materials, offering unparalleled insights into stellar nucleosynthesis, protoplanetary disk chemistry, and early planetary formation mechanisms. Its survival over billions of years preserves chemical signatures that would otherwise remain inaccessible, effectively acting as an interstellar time capsule from cosmic noon. The compositions observed in Three-eyed Atlas challenge long-standing assumptions about planetary system formation. Traditional models posit predictable patterns in young protoplanetary disks, where water ice dominates volatile inventories beyond specific distances known as ice lines. Yet Three-eyed Atlas inverts these expectations, exhibiting an extreme carbon dioxide to water ratio of 8.1, implying formation in a region where carbon dioxide ice exceeded water ice during planet-building processes. Standard models describe stellar nebulae collapsing under gravity to form central stars surrounded by rotating gas and dust disks, with temperature gradients dictating the freeze-out points of volatiles. Water ice beyond roughly 3 astronomical units, carbon dioxide farther out, and other compounds even farther. Three-eyed Atlas appears to violate these ice line predictions entirely, revealing planetary formation pathways that defy textbook assumptions. The chemical composition of Three-eyed Atlas indicates it formed in a region where carbon dioxide remained more abundant than water throughout the planet formation process, conditions entirely absent in our solar system and largely unexplored in conventional models of protostellar disk evolution. Simulations of protoplanetary disk chemistry show that achieving carbon dioxide dominance over water requires atypical stellar properties, disk compositions, or radiation environments. Three-eyed Atlas may have originated around a star with a different luminosity, surface temperature, or evolutionary history, altering the thermal gradients and chemical distributions in its surrounding disk. Alternative scenarios suggest stellar systems with unusual heavy element abundances, which in turn influence dust grain composition and gas phase chemistry. Stars with metallicities significantly above or below solar values can produce disks with volatile inventories radically different from our own, creating conditions where carbon dioxide ice exceeds water ice in planet-forming regions. These findings extend beyond the chemistry of a single object, raising fundamental questions about the diversity of planetary systems across the galaxy. If Three-eyed Atlas represents typical material from stellar systems born during cosmic noon, billions of planetary systems may have formed with chemical architectures completely unlike our solar system. This chemical diversity implies that habitable planets could emerge under conditions radically different from Earth, with atmospheres, surface chemistry, and potentially biological processes based on CO2-rich environments rather than liquid water. The survival and ejection of Three-eyed Atlas also illuminates dynamical processes within its parent system. Objects with atypical chemical compositions may interact differently with forming planets, influencing their final orbital distributions and the likelihood of being ejected into interstellar space. Recent exoplanet discoveries reveal planetary architectures far more varied than early theoretical models predicted. Hot Jupiters orbiting close to stars, super-Earths without solar system analogues, and unusual orbital arrangements demonstrate the vast range of formation conditions possible. Three-eyed Atlas provides direct Kinuit's journey into interstellar space, carrying its chemical secrets beyond the reach of spacecraft or sample return missions, yet its preserved substances may have played active roles in seeding planetary formation around young stars across the galaxy. containing materials older than our solar system itself, Three-Eyed Atlas functions as a traveling laboratory of primordial cosmic matter. With age estimates ranging from 7 to 14 billion years, the object harbors substances formed when the universe was less than half its current age. These ancient compounds have survived eons of cosmic radiation, interstellar chemistry, and gravitational perturbations, while retaining chemical signatures recognizable to modern spectroscopy. Preservation of such primordial materials demands protection from processes that typically alter or destroy chemical compounds over geological timescales. Cosmic ray bombardment induces nuclear transmutations that modify elemental compositions. Ultraviolet radiation cleaves organic molecules, and interstellar dust impacts erode surface layers while mixing materials from different epochs. The large size of Three-Eyed Atlas plays a critical role in this preservation. Its favorable surface-to-volume ratio shields internal materials from extensive cosmic ray penetration and surface erosion, a protection small interstellar objects cannot achieve. While smaller bodies lose primordial signatures within millions of years, Three-Eyed Atlas maintains sufficient bulk to safeguard its internal chemistry. The comet's nucleus has remained at temperatures near absolute zero during its interstellar voyage, effectively freezing chemical reactions and preventing thermal processing that could alter original compositions. This deep freeze preserves volatile compounds and organic molecules that would otherwise decompose under warmer conditions. Laboratory studies of meteorites and lunar samples demonstrate that space weathering can alter surface chemistry within thousands to millions of years. Yet Three-Eyed Atlas has endured exposure orders of magnitude longer while preserving signatures detectable through modern observational techniques. Its complex organic molecules, unusual isotopic ratios, and exotic volatile compositions reveal direct samples of primordial material from its formation epoch, effectively fossilized chemistry from early stellar nucleosynthesis processes. These preserved signatures offer an unparalleled window into the physical and chemical environment of the universe during its formative eras. Three-Eyed Atlas provides an unprecedented window into protoplanetary disk evolution and early planetary formation processes operating under conditions vastly different from those of our solar system. Isotopic measurements offer the most compelling evidence for primordial preservation. Different isotopes of the same element arise from specific nuclear processes within stellar interiors, producing signatures that endure through subsequent chemical processing unless altered by nuclear reactions. The isotopic ratios observed in Three-Eyed Atlas directly reflect the stellar nucleosynthesis conditions present at the time of its formation. The organic chemistry detected within Three-Eyed Atlas includes complex carbon chain, molecules and nitrile compounds that ordinarily decompose under cosmic ray bombardment within millions of years. The survival of these compounds after billions of years of interstellar exposure indicates either formation with unusually stable organic structures or highly effective protective mechanisms that prevented radiation damage throughout its journey. Comparisons with solar system materials underscore the extraordinary preservation of Three-Eyed Atlas. Meteorites from the asteroid belt, formed 4.6 billion years ago, show extensive alteration from solar heating, planetary interactions, and space weathering. By contrast, Three-Eyed Atlas retains signatures from potentially twice that age while showing far less alteration than typical solar system objects. The pristine nature of its materials enables direct study of cosmic chemical evolution, providing insights inaccessible through theoretical modeling or terrestrial laboratories. These ancient compounds may even contribute actively to the formation of new planetary systems. Three-Eyed Atlas could function as a galactic seed pod, carrying pre-assembled building blocks capable of jump-starting planet formation around nascent stars. Recent theoretical work by Suzanne Fallner and colleagues suggests that interstellar objects like Three-Eyed Atlas could address long-standing challenges in planetary formation theory. Traditional models struggle to explain how microscopic dust grains grow into planetary bodies without being lost to the central star. This difficulty, known as the meter barrier problem, arises because objects in the centimeter to kilometer size range experience strong aerodynamic drag from the surrounding gas in protoplanetary disks, causing them to spiral inward faster than they can accrete additional material. Three-Eyed Atlas bypasses this barrier entirely, providing pre-assembled kilometer-scale building blocks. Computer simulations demonstrate that interstellar objects captured by young stellar systems can dramatically accelerate the formation of giant planets. acting as condensation nuclei for the accumulation of gas and dust, and reshaping our understanding of planetary system assembly. Objects the size of Three-Eyed Atlas act as powerful gravitational seeds, attracting surrounding material far more efficiently than slow, incremental accumulation of dust and ice. Its unusual chemical composition provides additional advantages for seeding planetary formation. The extreme carbon dioxide to water ratio may deliver volatile inventories that complement rather than duplicate those in typical protoplanetary disks, expanding the range of possible planetary compositions and atmospheric architectures in young stellar systems. Successful capture of interstellar objects requires precise gravitational dynamics. Objects must lose enough velocity to become bound while avoiding collisions with central stars or ejection through planetary interactions. Capture probability depends on stellar system architecture, gas disk properties, and encounter geometry. Three-Eyed Atlas's massive size enhances its likelihood of capture. Larger bodies experience stronger gravitational focusing and greater cross-sections for interaction with stellar systems, while gas drag in protoplanetary disks more efficiently dissipates energy for massive objects, increasing the chances of achieving stable orbits. Statistical models suggest that encounters with interstellar seed objects occur frequently enough to meaningfully influence planetary formation. If interstellar wanderers like Three-Eyed Atlas are common, most young stellar systems could incorporate external materials during planet formation. The long-term survival of Three-Eyed Atlas demonstrates that such objects can preserve structural integrity and chemical composition across billions of years, ensuring that seeding materials retain their original properties when incorporated into new planetary systems. Evidence from meteorites in our solar system shows that Earth and its neighboring planets formed from chemically diverse ingredients, including material from multiple stellar sources. Isotopic ratios in primitive meteorites reveal contributions from varied nucleosynthesis processes, indicating that our planetary system arose from a mixture of local and extrasolar materials. The seeding hypothesis extends this principle across the galaxy, suggesting that interstellar object exchange may generate planetary systems with chemical diversity far beyond what a single star's protoplanetary disk can achieve. Studying this galactic recycling network requires coordinated observations from multiple space-based observatories. Every major space telescope is currently tracking Three-Eyed Atlas as part of the most extensive coordinated scientific campaign in human history. The international response has fostered unprecedented cooperation among space agencies, research institutions, and observatory networks that normally compete for limited observation time. More than 30 major telescopes, from survey instruments in Hawaii to massive mirror arrays in Chile exceeding 10 meters in diameter, redirected their programs to monitor this single target. Coordination began within hours of the initial discovery, triggered by International Astronomical Union alerts through the Minor Planet Center network, ensuring rapid global follow-up observations to confirm the object's nature and refine its orbital trajectory. The Very Large Telescope, Keck Observatory, Subaru Telescope, and Gemini Observatory synchronized observing schedules to provide near-continuous coverage as Three-Eyed Atlas traversed the sky from multiple geographic locations. Space-based assets, including the Hubble Space Telescope, James Webb Space Telescope, and the now-retired Spitzer Space Observatory, dedicated precious observing time usually reserved for distant galaxies and exotic astrophysical phenomena. These instruments offer capabilities inaccessible to ground-based telescopes, such as ultraviolet spectroscopy and infrared imaging at wavelengths blocked by Earth's atmosphere. The European Space Agency's Gaia mission, designed to map stellar positions across the galaxy, contributed precise astrometric measurements of Three-Eyed Atlas, enabling accurate trajectory calculations and insights into the object's origin within the galactic coordinate system. Gaia's unprecedented precision also allows detection of subtle gravitational perturbations, providing information about the internal mass distribution of the comet. Mars orbiters, including NASA's Mars Reconnaissance Orbiter, Europe's Mars Express, and the ExoMars Trace Gas Orbiter, were given special instructions to observe Three-Eyed Atlas during its October approach to the Red Planet. Coordinating these observations demanded complex orbital mechanics calculations to maintain spacecraft pointing accuracy while ensuring ongoing primary mission objectives were not compromised. Deep space. Missions such as Europa Clipper, JUICE, Lucy, and Psyche also contributed observations from unique vantage points throughout the solar system. These spacecraft provide perspectives impossible from Earth or Mars orbit, enabling stereoscopic analysis of three-eyed atlas's structure and composition. By combining simultaneous data from multiple locations, researchers can map gas and dust flows, examine tail morphology, and reconstruct three-dimensional internal structures, revealing details that would otherwise remain inaccessible. The Swift Observatory, initially designed to detect gamma-ray bursts from distant stellar explosions, redirected its sensitive ultraviolet instruments to monitor gas emissions from three-eyed Atlas. This adaptation highlights the versatility of modern space observatories to respond to unexpected scientific opportunities. Radio telescopes, including the Very Large Array, ALMA Observatory, and Green Bank Telescope, scanned for emissions at wavelengths where three-eyed Atlas might produce signals through natural physical processes or, speculatively, artificial mechanisms. These facilities offered complementary insights into thermal properties and magnetic field interactions invisible to optical instruments, providing a fuller picture of the comet's behavior. The scale of coordination required for this campaign demanded the creation of new data-sharing protocols, standardizing observation schedules, measurement processing, and result distribution among international research teams. Managing telescope time, data transfer, and scientific analysis across multiple countries and institutions presented unprecedented logistical challenges, demonstrating the extraordinary global effort mobilized to study this interstellar visitor. The rarity of an object like three-eyed Atlas underscores just how statistically extraordinary its discovery is. Professional astronomers use power law distributions to model the relative abundance of objects of various sizes throughout space, a framework validated by decades of asteroid and comet surveys within our solar system. These models show that small interstellar objects should vastly outnumber large ones. The detection of three-eyed Atlas, only the third known interstellar object, breaks these statistical expectations, challenging conventional understanding of interstellar populations and highlighting the exceptional nature of this discovery. The size distribution of interstellar objects is expected to mirror that of local asteroid and comet populations, with roughly 10 times more objects at each tenfold decrease in diameter. According to these models, discovering a 7-kilometer-wide interstellar visitor like three-eyed Atlas would normally require first detecting millions of smaller objects in the 100-meter to kilometer range. Current detection methods are biased toward larger, brighter targets that reflect enough sunlight to stand out against stellar backgrounds. Even accounting for these observational limitations, the probability of identifying three-eyed Atlas among the first few known interstellar objects approaches statistical impossibility under conventional population models. Independent research teams, using varied mathematical frameworks and survey simulations, reached similar conclusions. Monte Carlo simulations that model thousands of potential discovery scenarios consistently indicate that detecting an object of three-eyed Atlas's size should occur less than once per several million interstellar encounters under random sampling conditions. The pace of recent interstellar discoveries compounds the anomaly. After decades without confirmed visitors, 3 interstellar objects have been detected in just 8 years. This clustering implies either extraordinary coincidence or significant systematic changes in survey methodology. While improvements in detection efficiency, driven by machine learning algorithms and automated systems, have increased the likelihood of finding interstellar objects, these advances remain insufficient to account for the statistical outliers represented by three-eyed Atlas. Modern surveys achieve roughly 10 times better detection rates than earlier generations of astronomical instruments, yet this improvement falls far short of making discoveries like three-eyed Atlas statistically plausible. The comet's orbital characteristics further compound the improbability, introducing multiplicative rather than additive challenges to overall detection odds. Objects approaching from random directions should display a roughly uniform distribution of orbital inclinations, velocities, and approach geometries, yet three-eyed Atlas clusters near the ecliptic plane at a time that maximizes observational opportunity. Some explanations point to gaps in current models of interstellar object populations. Perhaps ejection mechanisms from planetary systems preferentially launch larger objects, skewing size distributions compared with solar system analogues, or gravitational focusing channels interstellar visitors into specific regions of space, enhancing encounter rates. More speculative theories suggest Three-Eyed Atlas belongs to an unusual population of interstellar objects with properties, size, chemical composition, and orbital behavior. Unlike any previously observed comet or asteroid, these statistical anomalies extend beyond individual objects, raising questions about the abundance and distribution of interstellar wanderers throughout the galaxy. Current estimates suggest roughly one object larger than 100 meters passes through the solar system annually. Yet high velocities and faint brightness make detection extremely difficult. The statistical improbabilities are eclipsed by the comet's exotic chemistry. Spectroscopic analysis reveals unusually high concentrations of cyanide compounds, indicating formation under chemical conditions previously unknown in our cosmic neighborhood. Ultraviolet observations from the Swift Observatory detected emission lines characteristic of cyanide molecules in Three-Eyed Atlas's coma, adding yet another layer of mystery to an object already defying conventional understanding of cometary composition. Cyanide manifests as sharp spectral features at specific ultraviolet wavelengths when molecules absorb solar radiation and re-emit light at frequencies determined by quantum energy transitions. Detecting these signals required advanced analytical techniques to separate cyanide emissions from those of other molecules present in the comet's coma. Because cyanide produces comparatively weak spectral lines relative to dominant species like carbon dioxide and water vapor, long exposures with highly sensitive instruments were necessary to achieve the signal-to-noise ratios required for confident identification. In space, cyanide typically forms through chemical reactions between carbon and nitrogen under particular temperature and pressure conditions. Its presence in Three-Eyed Atlas implies formation either in regions of its parent protoplanetary disk, where such chemistry naturally occurred, or through alternative processing during billions of years of interstellar travel. The relative concentrations of cyanide compared to other molecular species provide crucial insight into the comet's formation environment and chemical evolution. Three-Eyed Atlas exhibits cyanide abundances consistent with cold, dense molecular cloud environments, where carbon and nitrogen can combine efficiently without interference from competing chemical reactions present under other physical conditions. Laboratory studies show that cyanide molecules are usually unstable under space conditions, breaking down when exposed to ultraviolet radiation or cosmic ray bombardment over timescales far shorter than the age of Three-Eyed Atlas. The survival of these compounds over billions of years suggests either highly stable molecular structures or protective mechanisms that prevented photochemical destruction. While cyanide is detected in some solar system comets, it typically occurs at lower concentrations and exhibits isotopic ratios different from those observed in Three-Eyed Atlas, marking the object as chemically extraordinary and unlike anything seen locally. The unusual abundance patterns of cyanide suggest formation under nitrogen-rich chemistry, occurring in conditions markedly different from those of our local planetary formation environment. These differences may reflect alternative stellar nucleosynthesis histories or distinct protoplanetary disk compositions. The detection of cyanide adds a layer of biological intrigue, as while it is highly toxic to most Earth-based life, it also serves as a precursor for complex organic molecules that could participate in prebiotic chemistry under suitable conditions. Alternative formation pathways for cyanide include high-energy processes such as shock chemistry from supernova explosions or stellar collisions, where extreme pressure and temperature drive uncommon chemical reactions. Three-Eyed Atlas may therefore carry chemical fingerprints of violent astrophysical events that shaped its early history. Observations of cyanide emissions show time-variable behavior distinct from other molecular species, suggesting complex chemical processes occurring within the comet's nucleus as solar heating progresses. While some molecules display correlated variations, cyanide exhibits independent behavior, implying separate source regions or formation mechanisms. Future isotopic analyses of cyanide could constrain these formation scenarios, though such measurements require sensitivity beyond current spectroscopic capabilities. As Three-Eyed Atlas approaches the Sun, its chemical and physical characteristics culminate in a spectacular finale. Its massive size and unusual composition are expected to produce the largest comet tail ever recorded, creating a dramatic display visible across the solar system. Computer models predict that peak gas and dust emissions during perihelion could generate tail structures extending over 100 million kilometers, rivaling the distance between Earth and the Sun. These comet tails arise from interactions between solar radiation, stellar wind, and particles expelled from the nucleus during intense solar heating, offering humanity an unprecedented view of interstellar chemistry in action. Radiation pressure from sunlight pushes smaller particles away from the Sun, forming the characteristic curved tail that always points outward, regardless of the comet's motion. The extreme carbon dioxide production, observed in Three-Eyed Atlas, indicates that perihelion heating will trigger massive gas releases, far exceeding typical solar system comet activity. Current measurements of 129 kilograms per second of carbon dioxide could increase by an order of magnitude or more as the comet approaches the Sun, generating unprecedented volumes of material for tail formation. The retrograde orbit of Three-Eyed Atlas introduces unusual geometry compared to comets that travel in the same direction as the planets. This motion increases relative velocities with the solar wind, potentially producing tail orientations and morphologies never before observed in such detail. Early dust particle analyses reveal grain sizes and compositions unlike those of standard solar system comets. The unique surface chemistry may create dust populations with altered optical properties, scattering and absorbing sunlight differently, resulting in distinctive tail colors and brightness levels. Unlike smaller comets, the 7-meter diameter nucleus provides immense surface area and internal volume for sustained gas and dust production. Surface-to-volume scaling suggests that Three-Eyed Atlas could maintain high activity throughout perihelion passage, rather than quickly exhausting its volatiles. Multiple tail structures may form simultaneously as different chemical species respond to solar heating and radiation pressure in unique ways. Carbon dioxide, water vapor, dust particles of varying sizes, and even metallic vapors could generate separate tail components, each with distinct orientations, colors, and temporal evolution. Observers on Earth, in both hemispheres, may witness the three-tail system with the naked eye following the comet's emergence. From solar conjunction in December 2025, this display has the potential to rival historically bright comets that captured widespread attention. Space-based observatories will document tail evolution with unprecedented precision across multiple wavelengths. Ultraviolet imaging will reveal gas compositions and ionization states, while infrared measurements will map dust temperatures and size distributions throughout the structure. During perihelion, sublimating gases could trigger explosive fragmentation, creating multiple independent tails from separate nucleus fragments. Such breakup events occur when internal pressure overcomes gravitational cohesion, producing spectacular multi-tail displays visible across the solar system. Observations of this extraordinary display will establish protocols for studying the hundreds of interstellar visitors that future surveys are expected to uncover. Advanced survey telescopes will transform interstellar object detection from rare serendipitous events into routine discoveries, cataloging potentially hundreds of cosmic travelers each year. The Vera C. Rubin Observatory, commencing full science operations in late 2025, will revolutionize the field through systematic sky surveys, imaging the entire southern hemisphere every few nights with unparalleled sensitivity and automation. This single facility could discover between 6 and 51 additional interstellar objects over the coming decade. With its 8.4-meter primary mirror, the Rubin Observatory collects light from sky regions equivalent to 40 full moons simultaneously, providing survey capabilities far beyond previous astronomical instruments. Its advanced CCD cameras generate images exceeding 3 billion pixels, necessitating machine learning algorithms to process the immense data volumes and identify moving objects against complex stellar backgrounds. Automated detection systems, trained on millions of astronomical images, distinguish genuine interstellar objects from instrumental artifacts, cosmic ray hits, and other false positives, achieving detection efficiencies far beyond what human inspection can. Managed global coordination among multiple survey facilities will create networks capable of continuously tracking interstellar objects as Earth's rotation and orbit shift viewing perspectives. Space-based observatories such as ESA's Euclid mission, NASA's Nancy Grace Roman Space Telescope, and numerous ground-based telescopes will provide complementary observations, expanding coverage and precision. Next-generation surveys will detect interstellar objects at greater distances and earlier in their passages through the solar system, allowing extended observation periods for detailed characterization before they fade from view. Earlier, detection enables coordinated observations, across multiple facilities and opens the possibility for spacecraft missions to intercept particularly interesting targets. Statistical models predict that systematic surveys will reveal the true size distributions, compositional diversity, and population characteristics of interstellar objects, details that remain hidden when discoveries rely solely on chance encounters near Earth. This era of coordinated, automated observation promises to transform our understanding of the galaxy's wandering material and the processes that shape planetary systems far beyond our own. Large statistical samples will enable population-level studies that distinguish between different ejection mechanisms and the stellar systems from which interstellar objects originate. Current survey technologies suggest discovery rates of roughly 1 to 2 interstellar objects per year, with potential increases to dozens annually as detector sensitivity improves and survey strategies become more sophisticated. This shift from rare, chance encounters to routine discoveries will fundamentally transform how astronomers approach interstellar object research. Future space missions designed specifically for interstellar object encounters could become feasible once surveys provide robust catalogs and accurate trajectory predictions. ESA's Comet Interceptor mission demonstrates proof of concept for rapid response spacecraft capable of intercepting newly discovered objects during their solar system passages. Meanwhile, advanced spectroscopic instruments on next-generation survey telescopes will allow chemical characterization of interstellar objects at the time of discovery, reducing reliance on extended follow-up campaigns. Time-domain spectroscopy will track chemical evolution and activity patterns across entire solar system passages, providing temporal resolution unattainable with current studies. Machine learning applications will extend beyond detection to automated classification systems, flagging unusual objects for priority follow-up based on orbital parameters, chemical signatures, or other distinguishing properties. Managing the data from these surveys will require new computational architectures and storage solutions capable of handling petabyte-scale databases with real-time processing. Cloud computing and distributed networks will facilitate rapid response to time-sensitive discoveries. These routine detections are poised to reveal that interstellar wanderers may constitute the most abundant objects in the Milky Way. Objects like 3I Atlas could represent a typical member of a vast galactic diaspora, possibly outnumbering stars by enormous margins. Recent theoretical models suggest that planetary systems throughout the galaxy eject far more material into interstellar space than previously estimated, creating populations of wandering bodies that surpass stellar abundances by factors of millions to billions. Simulations of planetary formation show that gravitational interactions during planet assembly naturally eject substantial fractions of solid material into interstellar orbits. Giant planet migration, stellar encounters, and orbital instabilities can remove 10 to 90% of planetary building blocks from their parent systems, with multi-giant planet and binary star systems producing the highest ejection rates through three-body interactions that can scatter entire planetary systems into interstellar space, not extrapolating these ejection rates across the approximately 400 billion stars in the Milky Way produces staggering estimates. Conservative calculations suggest over 1018 objects larger than 1 kilometer in diameter wander between stars, creating number densities that far exceed stellar populations. The total mass contained in these interstellar objects may rival that of all stars combined when accounting for bodies ranging from asteroid-sized fragments to rogue planets ejected intact. This vast interstellar reservoir represents a previously unrecognized component of the galaxy's mass budget. Observational bias limits detection to brief passages through illuminated stellar systems, leaving the majority of interstellar objects hidden in darkness. Yet the chemical diversity implied by such enormous populations suggests that these wanderers carry samples from nearly every type of stellar system and planetary formation environment across galactic history. Variations in stellar mass, metallicity, age, and formation epoch combine to create chemical signatures spanning the full spectrum of cosmic element production and processing mechanisms. Understanding interstellar object populations demands new, theoretical frameworks for galactic evolution that account for the continuous exchange of matter between stellar systems through ejection and occasional capture. This cosmic recycling network may play a critical role in distributing chemical elements and potentially prebiotic compounds throughout the galaxy over billion-year timescales. Survival statistics for materials traveling between stars determine the fraction of ejected matter that remains structurally intact and chemically recognizable when encountering new stellar systems. Objects like 3I Atlas demonstrate that substantial preservation is possible, acting as cosmic time capsules, carrying ancient materials across interstellar space. Radio astronomy surveys targeting thermal emissions could catalogue interstellar objects invisible to optical telescopes, detecting bodies in the cold darkness between stars. Achieving this would require unprecedented sensitivity and survey strategies tailored to faint thermal sources against cosmic background radiation. Such investigations have profound implications for understanding how chemical elements and potentially life itself disperse throughout the cosmos. And galactic environment. Planets forming around stars of different ages and compositions would inherit chemical inventories far broader than those seen in our local neighborhood. Differences in metallicity between thick disk and thin disk stars illustrate how planetary chemistry evolved as successive generations of stars enriched interstellar space with heavy elements. 3I Atlas carries chemical signatures from epochs when nuclear synthesis occurred under conditions no longer present in today's. Galaxy.meteorite studies from our solar system show isotopic and elemental abundances clustered within narrow ranges, implying that our planetary system formed from unusually homogeneous materials. In contrast, the carbon dioxide to water ratio of roughly 8.1 in 3I Atlas may represent a typical volatile inventory for planets forming around stars with different masses, ages, or chemical compositions. Such conditions could produce terrestrial planets with atmospheres fundamentally distinct from Earth's nitrogen-oxygen, environment, habitability. Assessments for exoplanets generally assume water-based biochemistry under Earth-like chemical conditions. 3I Atlas demonstrates that alternative chemistries, based on carbon dioxide, methane, or other volatiles, may dominate across the galaxy. The preservation of these exotic chemistries over billion-year timescales indicates that alternative planetary chemistries can remain stable under space conditions, extending the potential range of biochemistry beyond Earth analogues. Future surveys of exoplanet atmospheres with next-generation telescopes may reveal that Earth-like compositions are the exception rather than the rule. The James Webb Space Telescope and successors could detect atmospheric signatures consistent with carbon dioxide-dominated chemistry observed in 3I Atlas. To truly understand planetary chemical diversity across the galaxy, we must move beyond the solar system paradigm and embrace the full range of possibilities revealed by interstellar visitors. These objects provide direct access to materials formed under conditions that solar system samples alone cannot replicate, carrying profound implications for astrobiology and the search for life. If most planetary systems develop chemical architectures unlike Earth's, then biological processes may follow entirely unknown pathways. Adapted to carbon dioxide-rich atmospheres and exotic volatile inventories, 3I Atlas is more than an unusual interstellar visitor. It is a messenger of cosmic chemical diversity, compelling a fundamental revision of our understanding of planetary formation, chemistry, and the potential for life. The detection, characterization, and analysis of 3I Atlas demonstrate humanity's ability to intercept and study these fleeting cosmic travelers, opening unprecedented opportunities to explore galactic chemical evolution directly. As 3I Atlas continues its journey into the darkness beyond our solar system, it leaves a transformed scientific understanding in its wake, establishing new paradigms for studying the vast population of interstellar wanderers, carrying the chemical heritage of our galaxy through the cosmic void.